Hello again, and welcome to another review session for your final exam in Calculus 3208. Or if you're preparing for the Calculus Placement Test, this will help you with that too, we hope. So here today we're starting Unit 7 in the course. Wow, we're well along. And Unit 7, of course, and this course is about antiderivatives and integration. So we're going to look at antiderivatives of power functions and polynomials today, after we talk a little bit about what an antiderivative is and a few of the details and rules surrounding those things. Okay, so here are the main topics for today. We're going to talk about the concept of an antiderivative, so what is it? Then we're going to talk about something called the most general antiderivative, and then we'll look at rules for antidifferentiation. So for the process of finding an antiderivative, we'll look at the rules that we have to obey for that. And then we'll look at how we take antiderivatives of polynomial functions. Okay? So it's not the world's most difficult topic, but it's an important one. So here we go. Let's remember differentiation. Differentiation is the process by which we find the derivative function for some other function. So let's look at this first line across the top here with all of these arrows that are moving in this direction. If I start with a function, f of x or y equals x to the power of 6, then the derivative of that expression with respect to x would be 6x to the power 5, just using our power rule. And then the derivative of that expression would be 30x to the power 4. And the derivative of that would be 120x cubed, and then 360x squared if we go one more time. So basically, if x to the power 6 was our first original function, then we'd have a first derivative, second derivative, third derivative, fourth derivative, and we could keep going for a while anyway. All right, now there is a process by which we could start from any point or any link in this chain here and work in the other direction. So go back toward the left. So let's see. Let's say I chose 120x cubed. Well, if 120x cubed is the derivative of 30x to the power 4, then we say that 30x to the power 4 is the antiderivative of 120x cubed. So basically, if I work backwards from derivatives to the functions they came from, this process is called antidifferentiation. So what we've done here is we've set up this chain in the opposite direction down below. So 360 x squared is our original function then, or original expression I guess in this case. Its antiderivative with respect to x would be 120x cubed. And its antiderivative with respect to x would be 30x to the power 4. And its antiderivative would be 6x to the power 5. And its antiderivative would be x to the power 6. So antidifferentiation is basically a process of working backwards from differentiation. Instead of finding derivatives, we're finding antiderivatives. All right. So are antiderivatives unique? This is an important question. So let's take a look for a second at all these different different functions over here on the left that we're going to take the derivatives of. They're all very similar. Every one of these expressions is x cubed over 3 and then plus some different number every time. Where this one would probably have a 0 added if you want to think about it that way. So what we're doing is we're just looking at the same expression plus or minus a different constant every time. Now when I take the derivative of those, and we all know how to do that, the derivative of x cubed over 3 is x squared. And the derivative of any one of these constants would of course be 0. So the derivative then of all of these functions would be exactly the same thing. It would just be x squared. Okay. Now, what does that mean in terms of antiderivatives? Well, it tells us that if x squared can be the derivative of all of these things, then that means that any one of these, or any number of other functions that have different numbers added or subtracted on the end, could be antiderivatives of x squared. So let's take a look graphically now at all of the possible, or at least several possible, antiderivatives for x squared. So over here is the same list of functions that we had, only they're not just expressions this time. We made them y equals that. So these could be functions for each one. And every one of those is graphed on this set of axes with a different line that corresponds to the same color we have in front of it here. And what you'll notice is graphically, every one of these functions is just a different vertical translation of y equals x cubed over 3. And you can tell from the graph that that's exactly what we see. They're just shifted up or down from one another on the graph. All right. So how is it that the antiderivative of a function like x squared, or the antiderivatives, are all just going to end up being vertical translations of one another? Well, we saw how that works in terms of the constant, the additive constant that we had over here, but how did that work graphically? Why is that the case? Well, let's think about this for a second now. Let's say I pick some value of x, like a number that's right about there on the x-axis. And I'm just going to draw a vertical line through there to indicate that all the points that touch that vertical line would have the same x-coordinate. Okay? Roughly, because I didn't draw a perfectly straight line, but you get the idea. All right, so now, what I'm going to do with that is at each one of those vertical, or each one of those functions where that line touches them, I'm just going to make a really quick sketch of a graph of what could be a tangent line that touches the curve at that place. Okay? And what you'll notice as I do that is that all of these tangent lines, all the way through here, with the exception of my not perfect artistic ability, but they would all have more or less the same slope, or exactly the same slope if we did this perfectly. So basically, we know that the derivative of this function at that point, or all of these different functions at that point, would be exactly the same, because the derivative only cares about what your slope is. So as long as I know the x-coordinate and I know the slope, that's all I need to get the derivative. Whether the function is shifted vertically up or down and how far makes no difference whatsoever to what the derivative is, which is one way to try to understand graphically why all of these different curves that are vertical translations of one another can have the same derivative. And then that should make sense to us why one function will have all of its antiderivatives as being the infinite number of possible vertical translations of the same function. Okay? So graphically, that's what an antiderivative means, more or less. Okay, let's move along. So we're going to talk now about the most general antiderivative. So a bit of notation for us first. We're used to saying that if I have a function f of x, and I take its derivative, okay? So I'm going to differentiate that. I take its derivative, I get a function f prime of x. And notice that when we write these out, we use lowercase f for both the original function f and its derivative f prime. Well, if I start with a function f of x, and I want to find its antiderivative, I want to move in the other direction more or less, what I do for that, if I want to find its antiderivative, is instead of adding a prime or something, because it's not like I can take primes away if there aren't any there in the first place, what I do is I just indicate it by a capital F of x. So when we use a capital F of x, what we mean is that that's the antiderivative of some other function that's a lowercase f. Okay? So basically then, if we think about that the other way, and you can see in this note that I have right here, the derivative of capital F is going to be lowercase f. All right. So let's get on to this talk about this most general antiderivative now that we have a bit of notation under our belts. It says if f is an big F, sorry, is an antiderivative of little f, then big F of x plus c, so this is a c, is the most general antiderivative of f. And we use a c to represent any arbitrary constant. So c can be any real number at all in the whole universe. So any real number added to that would be an antiderivative. So generally speaking, instead of giving a specific value for c, what we do is we just call it c, and then we have an idea about what that general antiderivative is. Okay, so specifically we could say that for the function we had before, f of x equals x squared, then its most general antiderivative would be big F of x, which is going to be x cubed over 3 plus any arbitrary constant. And that's how we'd write that out. We've got to put this plus an arbitrary constant business on it. Okay? So that's a big deal. It sounds like a subtle point. It's not very difficult, of course, but it's important that when we go from f, we get big F for an antiderivative, and we always have to add this arbitrary constant c to account for the fact that there are many possibilities. All right. Let's take a look at this now. All right, now over here on the left, I've written consider, and I've just listed a bunch of functions over here. So let's take a look at those. We've got f of x equals x squared, x cubed, x to the power 4. And next to them what I've done is I've written the most general antiderivative for each one of those functions. Okay? So let's check to make sure that they're actually antiderivatives by thinking about what their derivative would be and seeing that it actually gets us back to where we would have started from. Okay? So for the first one, we already saw that if I take x cubed over 3, I multiply by 3 and then subtract 1 from the exponent, I get x squared. In the second one, if I take x to the power 4 over 4, I multiply by 4, subtract 1 from the exponent, I get back to x cubed. And for the last one, if I take x to the power 5 over 5, I multiply by 5, it cancels out with the denominator, reduce the exponent by 1, and I have x to the power 4. So what we want to do is we want to notice a pattern here. And the pattern is sort of a relationship between the number we had in the exponent right there and these two numbers that we see in the antiderivative. So when we had f of x equals x cubed, we end up with x to the power 4 over 4. And when we have f of x equals x to the power 4, we get x to the power 5 over 5. All right. So if we look over here now, we've got some rules for antiderivatives. And the first one is, if we have x to the power of n as our original function, then the antiderivative is just what we get when we increase the exponent by 1 and divide by the new exponent that we got after it was increased. And of course we have to add the arbitrary constant to make sure that we account for all the possibilities. There is one little note here that I want to talk about for a second. It says n is not allowed to be equal to -1. Okay, let's think about what would happen if we tried to use this method for antidifferentiation when n equals -1. So if I have f of x equals 1 over x, or x to the power of -1, and I tried to follow this process to get big F of x, I'd have to increase my exponent by 1, and then I'd have to divide by that new exponent. Uh-oh, we are not allowed to do that. So this rule works for every real number exponent except for this poor guy right here, x to the power of -1. And how we deal with that, the antiderivative of 1 over x, or x to the power of -1, that'll come down the pipe in our next unit. But for right now, we're just going to remember that we can't deal with that function. We don't have a way to deal with that yet. Okay? All right. So let's look at a couple of other quick rules. The first one here underneath that says if I take two functions and I either add them or subtract them together, then to antidifferentiate that, all I get is just the sum and or difference, depending on what I had, of their antiderivatives plus an arbitrary constant. So that should make sense. That's pretty straightforward. Same rule applies for limits and derivatives. If we have the sum of the limits, we get the limit of the sums. And if we have the derivative of a sum, we get the sum of the derivatives. Same thing goes for antiderivatives. And the last one we have here is that any constant multiple of a function, its antiderivative is just a constant multiple of big F plus our arbitrary constant. And again, that should be pretty intuitive because the same thing works for limits and derivatives. So for antiderivatives, should be a-okay that works for us. All right. It seems really simple that these two rules are actually going to jive, that everything works fine with those, but it's actually quite important because what we're going to do now is we're going to try to antidifferentiate not just some really simple power functions, but some actual polynomials. And if we're going to antidifferentiate or find the antiderivatives of those polynomials, you've got to remember that polynomials are not just power terms like this. They could be power terms with a constant multiple in front. So instead of x cubed, I might have 5x cubed. And polynomials can have multiple terms that are added or subtracted together. For instance, I could be adding or subtracting 6x squared. So I need this rule as well to roll through that. But now that we have these three things, how to deal with a power function, the sum of two terms, and a constant multiple of a term, then basically we should be able to tackle polynomials. So let's go and try to find the antiderivatives of some polynomial functions. All right. So if I have f of x equals x squared plus 3x minus 7, well, we're just going to apply that power rule that we had to every term to get our antiderivative big F of x. So let's see what we have here. X squared, well, we already saw that one. It's going to be x cubed over 3. Plus 3x, we said the constant multiple doesn't make a difference, so we're just going to keep that around and deal with the x, which is going to become x squared, and we can put the whole thing over 2 if we like. Or if you want, you could write that as 3 over 2 times x squared. It's the same thing. And then we have to subtract. Okay, so 7x is really 7, if you want to think about it, as 7x to the power of 0. So you can increase that by 1 and get 7x to the power of 1 divided by 1. Or you can just remember that if this is a constant, its antiderivative would just be linear. Okay, so it's minus 7x. And of course, we always add our giant C as our constant multiple to anything on the end because there's lots of possibilities. All right, let's try the next one. F of x equals 7x cubed minus 5x to the power of 5. So our big F of x then will be 7x. I increase my exponent by 1 to the power of 4 divided by 4. And then I subtract 5x to the power of 6 all over 6. Okay? So not much to that. That's pretty straightforward too. And of course we have to add our arbitrary constant on the end. And for the next one, we have big F of x is equal to, so I've got 2x to the power of 8 is my first term, so that's going to be 2x to the power of 9 over 9, minus 6x cubed will become 6x to the power of 4 over 4, which I should reduce, and we'll do another step with this one, and then plus 17x, and then plus my arbitrary constant. So I'm going to just take one more step with this one to make sure I've got it reduced properly. So I've got 2/9 of x to the power of 9 minus 3/2 of x to the power of 4 plus 17x plus our arbitrary constant. Okay, and then for the last one, let's take a look. We're going to have capital F here of x will be equal to, so it's going to be minus 12x to the power of 4 over 4 plus 5x cubed over 3 minus 7x squared over 2 plus, it'll be 3x, and then our arbitrary constant on the end. By rights, we should take another step here as well, excuse me, because this negative 12 over 4 can be reduced. So we should take another step with that. I'm just going to clear a little space above it. Sorry about having to jam things together here. Should have decided to write smaller when I was younger and learned how to do it right. All right, so let's just get some of this out of our way. So if I write this a little bit smaller now, or just write the last step, this could also be said to be equal to, instead of 12 over 4, that's negative 3x to the power of 4 plus 5/3 of x cubed minus 7/2 of x squared plus 3x and plus c. Okay? So there's the antiderivative of this last one right here. Alrighty, so it's not rocket science. It's not terribly difficult. Rocket science comes in the next session. No, I'm just kidding. It's not all that difficult, but these are really subtle yet important things that we have to make sure we get nailed down. Alright, let's take a look at the your turn question now. So the your turn question here says find the general antiderivative for each one, and it's basically the same process that we just went through, only with some different functions this time. So a little bit of practice with finding antiderivatives of polynomials. And here's the solution for the your turn question. So all of those antiderivatives worked out for you. You get lots of fractions with these, but usually they're not too scary. And make sure you note that on every one we have to have this c, or this arbitrary constant that gets added at the end. Okay, and then we'll move along and highlight some of the key things that we talked about here. So some of the key things we saw in this session were that an antiderivative of a function f of x is another function capital F. In other words, capital F prime is little f. I don't know how else to say that. It looks better than it sounds. There are multiple antiderivatives for any function f of x, but they can all be represented generally by big F plus c, where c is an arbitrary constant. And to anti-differentiate a polynomial, we use these rules. So the power rule, which is increase the exponent by 1 and divide by the new exponent, and of course add a constant. If I have the sum of two functions, then I just have the sum of their antiderivatives plus a constant. And a constant multiple of a function is just a constant multiple of its antiderivative plus a constant. And that's basically all there is to it. Hopefully your studying is going well and you're going to be well prepared for all of your exams. Good luck and all the best. And if you have any questions, of course, post them up on D2L. I'll do my best to try and answer them for you.